join us today to learn about the quest for carbon neutrality and given some really innovative ideas on how we can move towards the future that we know we're all going to have to do very soon. And presenting for us today are two members of the company called Energy Machines. So they are in the business of what they're talking about, but their goal today is to inform us for our professional development about what's possible out there using one example of a solution that they've developed. So first of all, we have two presenters. One of them is Drew Alford. And Drew, I actually knew because he's been working with USACE projects over the last couple of years, and we've been lucky to partner with him when he was with a previous firm. But recently, he is following his real passion, which is exactly about what we're going to hear about. So something very close to his heart, and that makes it even more interesting. Drew is the client executive for the company Energy Machines. And Drew has been educated in construction management, and his new role at Energy Machines has him raising awareness of integrated energy systems and then driving that transition towards sustainable, high performance and elimination of CO2 emissions within the built environment operations. And to support Drew today in his presentation is the technical Director of Research and Development at Energy Machines, Lasse Thompson. Lasse was educated at Denmark's Technical University, and he holds a Master of Science in Engineering Physics and Applied Physics, as well as a PhD in Nanotechnology and Surface Science. Lasse has played a significant role in the continuous optimization of integrated energy solutions through his development of simulation tools and systems thinking. And Energy Machines today has a pretty comprehensive presentation for us that will probably run, I'm going to say about 45 minutes close to. However, they are going to leave time for questions at the end. And what I would encourage any of you to do is, if as you think of questions you might have, type them into the chat, just so you don't lose focus of them. Or also at the end, when they're done presenting, then you're also welcome to raise your hand and you can ask your own question. So either way you want to do that, but we encourage you to interact with them, but we'll kind of let them get through their story uninterrupted first, and then we'll discuss. So I'm really looking forward to what our presenters have to say. They will be presenting their own slides. And in the meantime, the rest of us can keep our cameras and microphones off so we don't use up the bandwidth. And with that, I will turn it over to you, Drew. Thanks so much for being here.
No problem. Thank you very much, Margaret, for the very kind introduction. And yeah, very, very pleased to be here. If I share my screen now, and then we can get into the presentation. Can everyone see that? There's no issue.
Yeah, we're
fantastic. Good. So Margaret's gave a very good introduction to both Lasse and I. Just to add to that, I'll introduce the systems as they are, and then I'll hand over to Lasse, who can discuss more of the technical elements of how the system goes together and how the whole integration happens. So just a quick introduction to the firm, and I won't go too much into this, but Energy Machines Group was founded in 2010. We're currently 67 employees, and we're a turnkey provider of integrated energy systems, which essentially are software-driven solutions that combine the traditional chiller, heat pump, ventilation, and domestic hot water production into one energy central. We've got 60 plus installations for BTS, and I'll explain BTS shortly, and 30 live installations of ATS. We've also, in our manufacturing facility, have produced over 1,200 heat pumps. So we're fairly confident. We know how these things work. Of course, we're always learning, and you never know. The information we can take from these sort of events can be quite valuable. So why we're doing what we're doing. Today, buildings are a growing climate problem. They account for 28% of the global CO2 emissions. USACE and the US Army Corps, including the Air Force and Navy, of course, are a massive organization. And what really appeals to me and why I followed up with Margaret on this was the impact that the US government can have globally, given that you're spread around the world. And so whilst they are a growing problem, and we can see the amount of square feet that are currently in the world, a global footprint in 2020, and where we're going to be forecasted for 2060, we also believe that they are a solution. So climate change will not wait. I'm glad that your current administration has rejoined or is rejoining the Paris commitment. We can see where the current policies are, where the pledges are, and where we need to be. So obviously there's some fairly drastic action needs to be taken. I think Bill Gates has come out saying that we can't do this without it costing and paying a premium. We would disagree with that. I think what we will demonstrate in the slides is that yes, you can go green, but you can also do it in an efficient manner and in a manner that actually makes sense financially. So integrated energy systems are a balanced thermal system that allows a building to generate, store, and reuse their own energy. Now, these numbers sound fairly extreme, but we'll go into them in greater detail soon. But an integrated energy system can lower your operating expenses by 80%, lower your energy consumption by 90%, and reduce the CO2 emissions for heating, cooling, and hot water production by 100%. And because it's a closed loop system, you also guarantee security of supply. Sorry, we've just got the visual going through. So how we create, and again, Lasse will go into the technical aspects. I'm just giving a brief overview. But an integrated energy system consists of electricity from renewable sources. Now that could be wind generated, solar generated, hydroelectricity. Anything that's a renewable source is important for the carbon neutrality. We aim to phase out fossil fuels, so removing gas and coal or oil burning heat production and cooling systems. We look to utilize local sources, which gives us that security of supply and also allows us to capture that waste energy, but store that waste energy, which is important for future use. Oh, sorry, my screen has just, sorry, one second, please. And here we are, back working again. And of course, it's one system that has a dual use. So this one system, well, should actually be a triple use, really. The one system can provide heating, cooling, and the domestic hot water simultaneously. We combine the heating, cooling, and the ventilation in symphony. This allows for the capture of waste heat instead of exhausting it out of a building, as is the traditional method of cooling a building. We actually take that waste heat, reroute that back in through the air handling units. It can via indirect evaporative cooling, we can lower the temperature, but you can also guarantee zero cross contamination, which is quite important for these COVID times. But then that allows us to have a supply air via the ventilation system that has a maximum temperature of 22 degrees Celsius, which I apologise, my Fahrenheit calculations aren't here, but I'm sure you, especially those in Germany, are used to dealing in Celsius. And of course, it's an intelligent use of resources. So through controlling systems, we monitor and optimize the system, and it's about being smart with how you move that energy. It's using batteries, for example, to support the electricity system, so we can shave peak loads off the electricity. All this leads to cheaper operating costs. So the main components are really the heat pump. So I appreciate we're showing an image of a heat pump that we manufacture. I will point out that our systems, it's a system design and it caters for many different variations. You don't have to use our systems, and we're not tied to them. If there's an equal or better pump out there that has similar specifications, we can easily swap them out, as can you if you adopt this methodology in the future. So the heat pump provides the heating and hot water and domestic hot water. We can do that all simultaneously. The heat pumps are run entirely on electricity, and so the carbon footprint is obviously attached to that. And of course, we can achieve we're also reducing the carbon footprint. We're achieving COP values, coefficients of performance values of 5, which for heating, if you combine heating, cooling, and the domestic hot water, you're seeing COP values of around 10. Now, I think some engineers would argue that the cooling is a byproduct of the heating; it's a waste product, and so depending on which side of the fence you sit on, it's a COP value of 5 or a COP value of 10. For those who are not familiar with the coefficients of performance, that means that for every 1 kilowatt hour of electricity, we're producing 5 kilowatt hours of heating. And of course, you need a source, an energy source, to feed this system. So we use multiple sources, and we combine some where we can. So the one that we've had the most experience with, primarily situations where there's bedrock, but also where there's limestone, is BTES. So this is borehole thermal energy storage, and I don't think this is foreign to USACE. I think you've perhaps dabbled in this system. I'm not entirely sure where, but I believe it's actually one of the largest systems in the world. But basically, the BTES is a grid of boreholes that are roughly 100 to 300 meters deep, based on the ground conditions, and they're 90 millimeters in diameter. You can drill them in a field, or you can also drill them within the basement of buildings. I've got an image of an installation later where we actually managed to drill within an underground car park. So there are lots of flexibility if you're challenged for space on site. It's a closed system, and we circulate brine we inject brine, to help extraction of the heat. Because it's closed, obviously it's quite environmentally friendly. As I said, it can be used in retrofit and new build scenarios, and we can design the system for single use. So if it's an independent office, for example, or we can design for surplus, so you can actually feed a base, for example, where you've got various buildings that have various heating and cooling demands and various surplus of heat generation. It can be an interconnected grid, which allows for the whole base to be running optimally. The second source, which we've also had some recent experience with, is foundation piles. So basically, the foundation piles, you insert a tube into the piles. It's a great, efficient way of doing it. Obviously, you take away the drilling aspect, but you are adding a slight additional cost to the piles. In both cases, they go to a centralized manifold, which then feeds the heat pump. Of course, you need to plan for this solution in your early planning, and so that's one thing to keep in mind. And as I said, the additional cost of the piles is offset by the avoidance of drilling for other systems. We are limited to the energy storage by the number and depth of the piles. However, that can be supplemented by other means. Another system is air to water or air to air. It's air to water. It's a heat fan system. One of the things you need to factor in is that these are a louder solution. They do work quite well in milder to warmer climates. There is no storage with these, so the efficiencies we gain will be slightly less, but it is an option, and one that you need to be aware of. Another option is a water reservoir. So obviously, if there's a lake close by, that can be used as a source of energy. But also another one that we've used quite quite regularly here in Denmark actually is ATES, which is Aquifer Thermal Energy Storage. So here we drill a series of wells, we split them into to heating and cooling storage. We have an injection well and an extraction well, which are typically 100 to 300 meters deep and roughly 300 to 450 meters in diameter. It's an open system which utilizes the ground conditions for the storage. This one here is particularly important that the ground conditions are favorable. Oh, and we seem to miss a slide here on the, apologies. Oh, I'm sorry, I'm not entirely sure. If you bear with me just for 1 second, please. I think I've touched the, I've managed to touch the wheel and and then the last one, sorry, is the internal reuse. So when you combine this system with a borehole storage or foundation piles or the water reservoir, for example, this is where you get the optimal solution. So this is where we capture the waste heat from the ventilation system and then feed it back in to boost the borehole storage. The beauty of doing this is that we end up with a 90% efficiency from the ventilation system, from the heat pumps, from the air handling unit. Sorry, traditionally you're comparing it to sort of a 60-70% efficiency. This also allows for us to reduce the borehole storage that's required, which will obviously have an impact on your capex costs. The internal reuse, coupled with the boreholes or foundation piles or the ATS, is by far the cheapest to run. In terms of how we produce the heat in the winter, obviously we utilize the storage. We take the storage up into the heat pump, and then we raise the temperature to the desired levels. Lasse can talk about this in greater detail later, and we've got some more slides. But then obviously that heat pump then circulates the warm air, also the warmth around the building. And then when it comes to summer, we often have an excess of heat, and the easiest way to cool a building is to remove heat. And so we reverse the system, and we take that heat and we store it in the ground in the thermal storage. And of course, within the ground, being an electric-based system, going back to that smart use of technology, we can, when electricity is cheap, especially if it's generated on site, we can actually utilize and run the system to charge the boreholes. So obviously in wintertime, you then don't need to lift the temperatures as high. An example here of a project in Sweden. I think Lasse, maybe you'd like to take over from here.
Yeah, I can do that. Excuse me. Yeah, so just to give you a more detailed view of something we have actually done. Then this is a shopping center just outside Göteborg, one of the main cities in Sweden. Here we have done a 700 kilowatt heat pump system, so 700 kilowatt heat output. We're integrating with the condenser heat, the reject heat from the supermarket cooling production, as well as the comfort cooling in the shopping center. We combine our heat pump with one of these board thermal energy storages. In this case, we have 81 boreholes of 200 meters of depth. This is combined with 550 kilowatt solar panels on the roof that over the year produce 76% of the total electricity consumed by the shopping center. So what goes on is, so this is a high-level pseudo PI diagram of our system. So you see we have the heat pumps here in the middle. We have two base load heat pumps that basically chills the cold system and delivers heating for the building. Then we have a top load heat pump here, which produces the hot water via this unit up here, and can also assist in peak load situations on the space heating system. So in this way, you can see we can run the system and simultaneously cater for all these different needs we have on the system. Yeah. So on the left side here we have the cooling coming in. We have both let's say comfort cooling and process cooling. So this is actually from of course the air conditioning of the building. So it's not using, for instance, rooftop units that blow away the heat from the condensers on the roof into the air. The reject heat there is routed into pipes along with the waste heat or the reject heat from the supermarket coolers as well. So this was a system they already had in place. Then during the project of building our system here, they were also integrating a new supermarket. So we decided to take that energy in here and on the yellow lines. So the yellow lines here is a subcooling circuit. So I will not go into all the details of what a subcooling circuit is. You're welcome to ask, but it's basically a way where we can integrate the higher level temperature waste heat sources in a very clever way. We can use some extra heat production from the refrigeration cycles in the baseload heat pumps and use that to produce our hot water way more efficient than just running from the cold side here directly onto the heating or the hot water temperatures. So then on top here you get the electricity use of the system and also what is produced by the solar PV panels on the roof. So just gonna play a little video. See the outside temperature is actually, I think this is below 0 Fahrenheit, right? Actually, so this this is pretty cold. This is minus 13 degrees outside, so it's a pretty cold winter morning. And what you can see is that right now we're dragging out heat from the energy storage. We have a little bit of process cooling from the supermarkets, and then we're delivering around these 500 kilowatt heating. So if I start the video here, you will see now it's around 8-9 o'clock, and now people will start going into the shopping center. So this is mainly the supermarket actually, where people go and pick up frozen peas from the counters and so on. We get a lot of process cooling. And actually what you can notice here is we get around 0, even a little bit plus sometimes during the day on our energy storage. So even in the middle of winter where we're still having sub-0 degrees, we are actually able to fulfill the cooling, the total heating need here just by taking this waste heat from the cooling of the supermarket, let's say freezers and refrigeration equipment. Also, you see we're delivering domestic hot water for the different stores during the day. So yeah, this is how we typically operate winter. During the night, we will go and take a lot out of the energy storage, but during the day, in this case, we can actually go and basically take all the heat we need for the shopping center directly from the waste heat. I think I need to go to. This is a little weird today. Okay, so here's a summer case. So of course, during the summer, we'll see a lot more solar production if you notice that during the day. We also have process cooling throughout the night because it's basically, let's say, still hot in the shopping center and still the supermarkets. Refrigeration needs a bit more cooling. And we load that into the energy storage. Of course, there's, I think there's more or less noise, but there's basically no heating demand. But of course, a little bit of domestic hot water need in the building. So when we start going up the morning into the noon, we see this cooling need starts to increase quite a lot. And now we load this into the energy storage because we have no use for it in the heating system. And of course, we take what we need for domestic hot water production here as well. And now you see the solar panels here really kicking in. It's a very hot day and sunny day, and we produce much more than the system used for electricity. So bear in mind that this one system substitutes basically the typical gas boilers or other ways to generate the heat for hot water production and space heating, as well as also providing cooling and managing the energy storage. So I think this is what we try to convey, is that we look at, let's say, heating and cooling as basically energy flowing in our system. That's why we call them energy systems, rather than looking as two different jobs that have no relation to each other. We see basically heating and cooling as let's say, moving energy and trying to preserve that in the best possible way. Yeah, so a little bit about what is our approach to let's say, designing these systems. What is our high-level philosophy and prioritization? So we kind of think that, and I'm sure a lot of you think the same way, that the best energy is one that you don't spend. So save on energy is let's say, present. It's always the best thing to do. So get efficient ventilation units with good heat recovery. Make sure your temperature controls are set in the most efficient way, etc. And that's just to say, never forget about these things, saving energy. So then, of course, when you have to spend energy, the way we like to do it is, again, looking at these internal energy flows in the building. So what is possible? So do you have some waste heat that you can move into space heating production or into hot water production? And we like to keep that, let's say, internalized in the building, in the campus that we are working with, because then we can also design the temperature on the different systems so they are efficient, working together with the heat pump. So one thing to keep in mind with heat pumps is that basically this cup value that Drew was talking about, the coefficient of performance. So this is the ratio of how much heat, or in principle, how much cooling you get out of using a certain fraction of a certain amount of electricity. So this efficiency can be, or cup value can be 6. So that's a efficiency of 600%. So when you have very low temperatures, you can operate this extremely efficient, this heat pump. But as you go higher in temperature, so here we are typically around hot water temperatures that we need to deliver, the efficiency of the system drops. And this is, let's say, not special to our heat pumps. This is just basically Carnot efficiency of the circuits that govern this trend. So if you can design your heating and cooling systems so they are with the least possible temperature lift, you will get a much more efficient system. Then let's say if we cannot directly move the energy, as let's say, as some part of the building needs cooling while another part of the building needs hot water production or needs space heating, then of course then we have to go to storage and recycling of the energy. So this is where the geothermal storages and battery storage come into play. Of course, here you have to think about the investment and the losses in the storage compared with how much energy you save. And finally, we look into, so here in Denmark and the Nordics in general, we have a lot of district heating and district cooling systems. So this, of course, we don't want to throw away energy even in that case. So then we look into setting up collaboration with these external energy flows, district heating, district cooling. The thing is, they typically operate at temperatures that are even beyond this graph. And for our system to be truly efficient, or the most efficient way to operate it, is down in these temperatures that are typical temperatures that we see for the space heating systems in the buildings. Then for the external flows, they typically operate up here. And this is, of course, still good to save the energy and use it somewhere else, but it has to have lower priority from our perspective. And then, of course, the last thing we want to do is put fan coils on the roof and just dispose of all our nice surplus energy. So how do we work? And I think this is common to a lot of people in our business, how we work with these kind of systems. So we understand that, let's say, we are sometimes disrupting a little bit the current way of looking at things, and we typically get asked to provide some kind of business case to our customers so they can understand, okay, if you do all these things, that all sounds really great, what is going to be the business case of this? So we gather the knowledge that we need and the demands for the building, and then we select the heat pump based on this and do an overall storage dimensioning, and we investigate synergies with renewable energy. And from this, I think it's the next slide, yeah. But with this, we can basically perform system simulations of these scenarios, these high-level designs that we put together. From that, we can calculate the energy consumption of the system, and from that again, we can calculate the OPEX, the operating cost of the set scenario, the set high-level design, and compare that to the reference case, the status quo of the building. And in this way, we can provide, let's say, decision-making material for the client to be able to hopefully decide on going forward with such an integrated system. So here's just a little snapshot from the simulation. But typically, when we talk about demands, what is it we look at? We look at duration diagrams. So we look at what is the peak power that the building needs, in this case around 400 kilowatts for heating and 300 kilowatts for cooling. And then we see how much energy is basically the area under this graph. It's very important to, of course, size the heat pump correctly. We can also look at how much of the energy can we cover by the installed capacity of the system. So sometimes we have scenarios where it makes more sense to have an electric peak boiler, for instance, taking care of the peak. You can see, for instance, for heating, you can provide quite a very large percentage of the energy by just having, let's say, 75 or 80% of the peak capacity. We look at what kind of temperatures do we need in this building to provide the heat. And of course, we also look at the energy and cooling demands in energy over the different months to figure out how to best fit the system. Then to select the heat pump, we run simulations against these demands. So here's we run a simulation where you can still see we have some peak demands for the heating, provide the red here with the heat pump, and actually also some with the subcooling circuit I was briefly mentioning before, and we'll provide all the cooling here. So we can of course aggregate that up and say something about how the OPEX of the system is. We also look into how is the ground storage performing. So here we see how much energy we will be taking out of the ground in winter and how much we will feed back into the system during summer. And we discern between two types of cooling. We have the green, which is free cooling, and the blue, which is active cooling. So when you have the ground, you can actually take advantage of this being, especially in the spring, colder than the typical temperatures you need to supply into the building cooling system. And when you do that, of course, you just circulate the water basically through a heat exchanger and then circulate it through the ground to cool it down. So the only energy you spend is what the circulation pump is doing. So here you can talk about COP values from 20 to 40 on the cooling. Whereas when you go into the active cooling, this is of course when the ground starts to become hotter than the temperature you need to supply to the building. In that case, you use the heat pump as a chiller and run it. And of course, this generates a lot of heat that you can use otherwise in the building if it's needed. But let's say, of course, it's from a cooling only perspective. Then you run the heat pump as a chiller, so you do spend some more electrical energy. And if you, let's say, only look at the cooling as a resource, then your COP value is maybe around 4 to 5 to 6 in this case here. Then, of course, I don't know in the US or where you are based, but there has been a lot of concerns about these ground storages, let's say, cooling down too much and so on. So we also do simulations, 25-year simulation of how is the temperature changing in the ground. Is it going sub-zero, but hopefully, or not hopefully, but in this case, not too much. It's still within good reason. So this is also something we need to look at in every project to make sure that we design the ground storage not too large, because it's a big investment, of course, to do the drilling, but we also need to not design it too small so that you end up in a situation where you cannot deliver the energy that the building or the set of buildings need. Then we look into the synergies with renewable energy. So here you see the different consumptions on top here of the zero line. So basically we have a consumption for building operation, computers, coffee machines, copiers, whatever you got. We use some energy for ventilation, and we use some energy to run the heat pump. So it runs here in winter, of course. A lot of electricity is used for when we're generating heating, and then during the summer also a little bit is needed for this active cooling, whereas in the spring and autumn months where there's of course the least use of energy. Then we can put in batteries to see how they contribute here. So here you see we take out some energy to charge the battery, and then we and then we can actually deliver it in here to make sure we are not buying too much energy from the grid. If the customer have, let's say, a goal of not doing that. So here you see the orange is all the solar production that basically offsets all the energy spent here, and we're even able to sell a little bit of electricity. So the reason why we in some months both sell and buy electricity is of course that the sun is not shining during the night, and we have the battery can sometimes go to zero charge level in this case. So then we have system design. So basically we have gathered after a lot of doing a lot of systems. We have kind of gathered our standard set of modules. So this is the different modules for the heat pumps that we basically pick the right size that we need based on our sizing, and then we combine it with different modules. So we have modules for the ground storage, we have modules for the different chilled system, heat recovery, storage module, chilled system connection, and so on. We have also a module to recharge the ground from other types of sources, and then the red here all the modules that we have or some of the modules we have from the hot side, how to deliver the energy, heating energy to the building. So then basically we assemble the puzzle, and we have a system designed this way. So the reason why I say all this is, of course, these integrated systems can seem, let's say, very complex, and they can easily start to go off in a direction that look very one-offish. And we of course want to industrialize this integrated energy system, so it goes from being this big, complex, possibly highly effective or efficient system, but goes into something that is industrialized, something that you can actually, let's say, relatively easy design and put together. So this is the thinking behind this modular system approach that we have been building. And here, just to show, this can be a basic one of our larger systems we have put together. So this, let's say, another part of the design phase is to provide a full PI diagram of the system and how it interacts with the different consumers in the building. So when we're through the system design phase, we of course quote the system to the client, and if they go forward, we get into to implementation. So here I'll say a little bit about how we establish the board thermal energy systems and fitting of the energy central. So just to make it a little bit more tangible, what all this drilling is about. So this is actually a picture from this project, the shopping center that we showed before. This is from this Frölunda Torg shopping center, where they had an old car park. So the shopping center was of course already built and in place when we got hired to do our system. So there was no, let's say, land area beside the building, and we had to be creative. And basically using this special drilling technology here, we're able to drill in this old car park. And as you see, this column here is the main drill. It's about, I guess that's 4 inches, 10 centimeters, 9 centimeters in diameter. And this is basically, let's say, the size of the holes. So one common misconception is that these holes are where we store the energy. So this is actually not the case. These holes we drill deep into the ground, 200 meters, in order to put in a plastic pipe that we can use to circulate a brine. That is the energy carrier that goes to the heat pump. But the hole itself is not very big. It's not going to have a lot of energy. It's actually a heat exchanger that allows us to interface and activate a big portion of the ground below the surface. So this is also why we do a grid. It's basically because the total volume of this grid that we span out in typically a square or rectangle, and then the depth we drill to this kind of box of ground, that whole volume is basically the energy storage. So when we talk about how much energy we can shift from winter to summer, we talk in gigawatt hours typically, whereas typically surface tanks with water, they store energy on the scale of megawatt hours, if that even. So the ground storage is a very, very large storage that you can do that way.
Sorry about the resolution. It looked better on the screen.
Yeah. So this is a shot from one of our energy centrals. So you see, we have done some work here with different colors of the piping to show, let's say, users what is the different cooling going on here in the blue pipes and heating in the red pipes, of course. Yeah. So, but typically our implementations go inside an energy central, a large technical room in a basement, can also be on a building aside from an already existing building. Of course, we can also actually put a lot of this equipment on the roof if necessary. But let's say, I know in the States there's a lot of decentralized systems, whereas let's say to really gain this synergy between heating and cooling, we take all the energy back to this central energy central. Yeah. And here you can see a 3D design of one of these systems. So in this case, this is for a large IKEA warehouse in Sweden, where we have 5 of the base load heat pumps. So 3 of them is actually running both for heating and heating and cooling generation. And then their cooling peak load is much higher than their heating peak load. So the last 2 is primarily installed for cooling. But because they're so close, we basically hook them up also for heating. So they have a massive redundancy here in the system, which is of course always a very nice thing. And then you have the hot water production heat pumps over here. And of course a lot of piping to connect this. And then operation. So this is also, as we see it, a very, very important part of the life cycle of such a plant here is basically, I think we have 5 minutes left of the 45 minutes. Yeah. So operation and continuous monitoring and optimization is really the headline here for us. So we connect all our systems to a cloud-based logging solution. Can of course be on-premises cloud or on-premises server room, but we connect them to our cloud system where we can basically monitor and view the performance of the system as it goes. So of course there's a lot of great things about this that let's say the client's technical people will get access to this at the same time because it's in the cloud. And web-based, then we can look with our experts on the same data synchronously with the local technical people, and in this way help them out, optimize the system, and solve any issues. It also have the advantage that that basically we can look at an ensemble of systems, and in this way we can compare how they operate because we have all the data available in one place. So we think that because heat pumps, all the stuff I talked about, let's say, of course, you have a very integrated system, but also what I talked about, that the temperatures you use in the heating system and the cooling system is important for the system efficiency. Then we like to stay, let's say, in connection with our systems and keep advising the customers and checking that everything is operated to ensure the best performance of the system, really. Yeah. So one thing I think we are not the only one that provide this solution, but one thing that a lot of these heat pumps that get sold, they have very fancy numbers for the efficiency, also chillers, fancy numbers for the efficiency and how they're supposed to operate. So there's different ways you can do this, but basically if you look at the thermal properties of the refrigerant and you have enough measurements of pressure and temperature in the refrigeration cycle, you can basically calculate the state of the refrigerant in each part of the system, and from that you can derive how much power are you actually delivering through the heat exchangers at any given moment, and you can actually derive efficiencies for the compressors, and you can in this way also get all the way and show the cup value, the efficiency of each individual heat pump as it's operating. So this we see a great value for the client in this transparency and being able to really look at how these systems are performing online, not through some yearly aggregated energy measurements on the electrical bill or something like that, but every minute update how is the system actually operating and how is it performing in the live situation. This is really where you get access to debug and optimize the system to make sure that it's operated as efficiently as possible, in our opinion. So I'll just end with another little case study. I think I have 2 minutes left for that. So this is a hospital up in northern Sweden, in Umeå. They installed one of our heat pumps, 1.2 megawatt system, basically in order to be able to take advantage of all the surplus heat from their cooling systems. So a hospital has a lot of medical equipment that need a constant cooling, and of course it's also operated 24/7. So they have a lot of surplus heat from that they used to blow away on the roof on fan coils, and they wanted to see if they could use that for basically heating the hospital. So basically what we achieved is that the hospital is basically now 90% heated by their own surplus heat from cooling. So imagine this, only 10% of the heat needed in northern Sweden is supplied from outside, and 90% comes from the processes just in the hospital. And as you see, it's not new fancy low energy buildings. It's of course very well insulated buildings, but from the 80s that are there basically, and still this is possible. So when they started out, this was the 28th biggest geothermal installation in the world, and they save over 10 million Swedish krona, which is $1 million US dollar, I think, per year in energy costs. So even though this is state-owned and they have a district heating system in the city, of course the state still looks for cost savings to basically provide more healthcare for the same amount of money. And so even, let's say, looking at the internal cost for district heating, they could save a lot of money. And of course they eliminated a lot of tons of CO2 doing this as well. So what you see here is that this hospital is kind of like a campus-style hospital. Our heat pump is well, actually we have several of these installations, but the one I'm talking about here is the main one, 1.2 megawatt in this building. I think it's this building, which what you see here is basically the cooling loop. So this is a thermal network, they call it, where we send water around at 9 degrees. So 9 degrees centigrade is what is needed for all the hospital equipment and for the decentralized fan coil units inside the wards to provide comfort cooling in the summer. And then all these red points are basically heat pumps that are able to drag this heat out of this cooling thermal network and use it for something smart. So for instance, this big site here, we use it in collaboration with this energy storage to basically provide a lot of space heating for the building. So here you see the PI diagram of this. So here you see you got a 500 kilowatts of surplus heat coming in here from the hospital. So okay, this is not the coldest point, but even a winter night up there minus 20 degrees, so well below sub-zero Fahrenheit degrees, you still got around 300 kilowatts of free heat coming in to the system. So again, I think you recognize this from the Frölunda talk reference case also, that then what we cannot get from the cooling system in terms of heat, we take that from the ground. When we have a surplus, we put that back into the ground, and then basically we deliver the heat over here on the heating systems, and we provide the hot water for the building as well. What you see over here in this duration diagram is basically, this gives a good view of how much of energy can you move. So they have a total heating load need of 9.3 gigawatt hours per year, and this heat pump delivers 8 gigawatt hours of this heating energy over the year. They also have 5 gigawatt hours of cooling demand that we also transport through our heat pump here. And so where it gets really interesting is where you have this purple part in the bottom here, because this means we have a cooling demand at the same time as we have a heating demand. So then we don't even need to use the storage here. We basically just let the energy go through the system using the heat pump. So it's simply a matter of taking waste heat at a lower temperature, upgrading it, and delivering it out as valuable heat on the other side of the system. Then, of course, the difference between the what is here and what is over here is then stored and then retracted again from the ground. And then this again decides the system to be the most financially viable. So above here we use the district heating provided by the city for the peak load, and then over here we have other heat pumps in the system that are configured as chillers that will then get rid of this energy here. Today they are continuously expanding on the heat pump part of this network to really go and be completely self-sufficient. And even they think they can drag so much energy out of the hospital that they can start supplying a neighboring low temperature grid to houses next to the hospital. Yeah, so that was our presentation. So yeah, thank you very much for listening.
So Drew and Lasse, that was a really fascinating presentation. I think you struck just the right mix between technical and layperson understanding to make it very palatable for the wide audience that we have. And I know I learned a lot, and I appreciate you sharing that. So we do have a couple of questions that are coming up in the chat. I'm gonna, since I'm the moderator, though, I'm gonna ask the first question, which while people are thinking about some other ones, is does this, like in general, is this gonna work better in certain types of buildings or facilities than others? And where do you think we stand to get the most benefit, and as a society should focus these efforts first?
Yeah, I think there's definitely cases that lend this very well. I think these campuses where you have this heterogeneous, let's say, demands, where you both have the need for space heating, for offices, wards, storage facilities, whatever it be, and you also have equipment that needs cooling. This is really where you can just, in the same instance in time, you can move this wasted heat from the cooling processes and upgrade it via the heat pumps and supply it into the building as valuable heating that you would otherwise have to generate from gas or buy from district heating or whatever your sources are. These are the great cases, of course. So shopping centers, hospitals, if you have a, let's say, factory close by where you have some living quarters, you have some residential areas nearby. So you get this synergy between the cooling and the heating. Of course, you also have to consider the local ground conditions. You have an aquifer available, you have good ground for drilling, and so on. But yeah, I think really these bigger campuses or bases, I would say, almost, right, where you have these different usages of buildings generating cooling throughout the year, or waste heat from cooling throughout the year, and also needing the heat. Yeah.
That makes a lot of sense. And so obviously then a follow-on would be, when we're building a new, an entirely new campus from greenfield, then that would maybe dictate placement of facilities as well to be within range to take advantage of those heterogeneity, I would think. Yeah, very interesting. So we've got some questions in the chat and we've got hand raised. I'm going to start with the first one I saw, which was in the chat, and Gary Russ, who's a U.S. government employee at the U.S. European Command, is asking about if there's plans to develop a heat pump exchange mobile system.
Yeah, actually, I think we have quite a lot of ideas where we see a lot of retrofit projects where the building is already there, and we need to come and get rid of gas boilers and stuff like that. Then we are designing a modular concept, like basically like a container concept, where all the modules are aligned with what can you transport on road, and then you basically can crane in this energy central that we're talking about and hooking it up quite easily on site. So I think that could be extended to be like more like a mobile thing if you have like a temporary base or something that you move around. Yeah.
And is that what you were speaking of, Gary, or did you have further follow-on?
No, you're spot on. Obviously, I'd be very interested. What the presentation is about installational energy, and as you can appreciate, sometimes we need operational energy as we deploy and do various things.
Good, thanks. And Michael Otensman, you have your hand raised. Go ahead and ask your question, please.
Yes, I had a couple of questions. I come from the energy program also from the Air Force side. One of the things that has been very typical for the DoD energy program is payback. What is it when you retrofit a system like this? How many years roughly does it take before the energy reduction in energy costs pays for the system?
Yeah,
the Frölunda 12 project, the one where we drilled within the car park, that one had a payback of 7.5 years, I believe it was. Another project was a 33,000 square meter office building, which was, I think, 7.8. And just to be fair and transparent, not every project is going to be like that. So we have a project in Denmark where it's a crazy project that we're having to try and lower the drilling rig into a basement down a staircase, and access is poor. We don't have any access around the building to drill. and that one there sits around an 11 to 12 year payback. So just to be open that it's not they're not all sort of between 5 to 8 years. They're sometimes a little bit more, but it depends on what your ambitions are. If you're going for CO2 savings, or if you're driven by operating cost savings, we can work systems the system can be worked to fit your needs.
I would say there are three main things to consider. It's the local energy prices, of course. What's the price of electricity versus your, let's say, current source of energy? And then you need to consider, let's say, what are you aiming for? Are you aiming for, do you have this great synergy between cooling and heating we had in this hospital? And do you stay on that level where you just transport energy? That's you only have to invest in the heat pump. And then that's, of course, a very short payback time, because that runs a lot of time during the year. Then adding the storage onto that will, of course, let's say, weigh down a little bit this investment side of things. Yeah. So yeah, I think I had a third, but now I forgot.
Okay, but on the whole, actually, that's very reasonable. That's not overtly expensive in terms of a payback timeline. So depending on the project, that certainly would be within the realms of a reasonable investment historically. The other question I had was concerning the actual net zero itself. And typically in the Air Force, there have been energy programs in the past, the LEED certification, the Energy Star certification. Is there a net zero carbon certification program in the works? I mean, I know there are agencies that will certify your project as net zero carbon, but are there any certification programs per se, like a Energy Star, like a LEEDs, that you're aware of?
I think we would fit into those. Obviously through the monitoring system, we can provide hard evidence of the transference or use of electricity. Of course, if it's coming from a certified green source, then that's quite transparent.
I think it's typically from the building side, right, that we see there's quite a lot of these DG&B, for instance, have this where you can choose a level on that. They have gold and platinum and so on, but it's also the way, if you want to achieve very high grades, you can go into a path where you ask for third party, let's say, verification throughout the commissioning process and the implementation part of the process. So you get this third party validation, which gives you a lot of points in this particular, let's say, program.
And so, Mark, just one comment on the payback that's just sprung to mind. What we find is that the level of operating cost savings, and because of the shorter payback, you can actually fund or finance these installations through OPEX savings only. So primarily we're working with private clients, but we've run a number of scenarios where we'll actually fund the installation ourselves. Now, not necessarily saying we do that by US Army, but we actually fund the installation ourselves, and we take that operational risk, and we say, okay, 10 years, we will, if this isn't paid back through OPEX savings in 10 years, then that's your win. But it's on us then to optimize the system and to make sure that it's running at its most efficient. But
yeah, there have been.
Yeah, just to say that it is possible to fund these things, especially with interest rates being quite low at the moment.
Yeah, there have been several programs that at least the Air Force, and I assume the Army, has done in the past to do exactly that. So that's very useful information. All right, thank you.
Thanks, Michael. Scott Turrigan writes, he says, this is not a question, but he would like to point out the value of these systems to military type facilities. Systems like these that make facilities and installations more self-sufficient are valuable to DoD's mission assurance objectives. Being self-sufficient reduces our mission vulnerabilities, to infrastructure dependencies, which are often outside of our control and have vulnerabilities in the distribution network to our facilities. This is especially concerning on bases which are outside the US, where we have even less control and the host nation can purposefully disrupt our delivered infrastructure dependencies when political opinions are at play. So yes, that's a very good point, Scott. Scott, that's in Scott's scope of duties to be aware of these things. So I'm sure that's very interesting for him. Scott, did you have anything else you wanted to add or any questions?
And from our side, I mean, just to build on that, and with your friends Russia, we're working with IKEA and investigating their Russian portfolio, and there it makes no financial sense because gas is so cheap, but it accounts for a third of their CO2 production globally. But what we're doing is by creating that independent closed system, we're now free from reliance on the Russian gas network. Now, if you're familiar with Europe, as I'm sure most of you are, a lot of our gas is coming from that part of the world, and so yeah, from a security supply, it's a great option.
Yeah. Margaret, do you want us to go ahead and answer some of the questions there? Or?
Yes, yes. Matthew Marosek asks, what is the typical useful lifespan of the system?
So typically the ground energy storages is around at least 50 years, but as long as you dimension them and you keep this balance between heating and cooling, they can pretty much go on forever. And the heat pumps themselves are typically 15 to 20 years. That's a rated lifetime of the compressors inside, which are the main part. And probably by then more efficient compressors will have been developed. So it makes sense to change out the whole heat pump. But yeah, something like 15 to 20 years is typically what we use in calculations.
And also, I mean, you sort of spoke about this earlier in terms of the cost, but I mean, these are various components, right? So do you have if a customer comes and maybe can only incorporate portions of the system at a time, do you have like a phased approach where you'd recommend, okay, start with this module and then add this component and then this one? Is it work like that?
I mean, that would be great. I think, of course, every project we would think like that in reality, right? But yeah, I guess you need the heat pump, right? And that's the main part. And of course, you can configure that to run as a chiller only for a certain number of years, and then when you have your heating system connected, then you can start delivering the heat instead of getting rid of it. But it could also be something like starting with one base load heat pump and take the part in that duration diagram I showed that is basically moving energy from one system to the other continuously. That's again also from investment perspective, lowest investment with the highest payback, most bang for the buck, I guess it's called. And then when you get familiarized with that, you think that's great. Then you can add the energy storage. Then you can start going high in this duration diagram, and then add another baseload heat pump, add the hot water production heat pump. That should be possible. Of course, there's some physical restrictions in the energy central, and of course planning everything out before really well, and then going for implementation is always, let's say, the cheapest when you look at it that way. But of course, in reality, things might change. I mean, we've also done systems where let's say we actually split out before the heat pumps. So we take the energy storage and we connect that to multiple buildings directly. So each building gets their own separate heat pump that is matched to the heating system. so we don't have to drag hot water around the campus. But again, we just take these uninsulated pipes for the ground source and then share that with multiple buildings, where we then place, let's say, decentralized heat pumps in each building.
And I guess in that scenario, you can always add additional boreholes.
Yeah, of course, you have to think about like the main infrastructure, your pipe highway down the middle of this campus. What kind of pipes do you want? What kind of level of water flows and energies do you want the system to be capable of delivering? That's of course something to think from the beginning.
Great, thanks. That's exactly what I was thinking about. Are there anybody else have a question on the top of their mind? Raise your hand. I want to point out also, I'm posting a link right now into the chat, which is a link to the Corps of Engineers, Engineering and Research Design Centers, MILCON something. I forget what MISRI stands for. MILCON, I just can't remember it right now, but it's a group within ERDIC that publishes things like the UFC, and that link will show you the different centers of standardization, and there's a section on sustainability, and it gets into quite a lot of this sort of knowledge base. They have references. It's even a place that Energy Machines could post their tools as an option. It's a place where, you know, collaboratively designers can go and get information of this nature for the benefit of U.S. government facilities and those that design them. So check that site out if you want. It's also got a lot of POCs for use there to be trying to connect the community. So I also noticed that Cherise posted a link in the chat to our Rhein-Main Post website, where you can later come back and see the slides from this presentation or the entire recording that you can refer to others to listen to when they have a chance. That's what's nice about doing things virtually. So, okay, I think we're close to wrapping up our session today. And I very much want to thank both of you, Drew and Lasse, for joining us and sharing your knowledge with us and increasing our knowledge. It's really been interesting. And we hope we'll see you again at our post. You're always welcome to join us to learn about some other things. And given that, I'll turn it back over to Cherise.
Thank you, Margaret. Thank you, Drew and Lasse. This was a very, very interesting presentation. And Margaret, thank you for sharing the resource information. That was good. And appreciate the comments from Scott and Gary and Matt, too. This was a great presentation. Thank you for your time. Thank you, everyone, for joining. And we hope to see you at our next meeting.
Okay. Thank you very much.
Thank you for the opportunity.
Yeah.
Bye-bye.
Take care, everybody.
Take care. Bye-bye.
Bye.